All right, so now we're going to get into the diary entries that I started when I began this whole project. Hopefully, it gives a little bit of an insight into things that you would encounter when you're trying to build something new and the kind of frustrations and all that that might happen, but also ways of solving those problems and come up with solutions. So, first of all, one of the things that you're going to see is a reference to a project called Amy Agma. That was the original name that I gave the project. Amy is short for Audio Machine Intelligence. That's our machine learning framework over at Bon Jovi Media and Technology. Agma was the code name that I came up with for the project. So I thought that was a really cool name, but you know, as things go on, you realize those really cool names have been used before in the space. Another name that I really wanted to use was called Zanshin, because in Japanese that means a mind that is finished with a task but is ready to resume and is always aware, sort of like what this framework is all about. But I can't use that because other karate nerds like myself also like to use those great words. So the project is officially called xaq-ai. That's just a handle I've used since I was a kid. It's just a fun name. Doesn't mean anything. You just read it. XAQ. That's what it is. So my experience with AI goes all the way back to 2014. I just got very, very captivated in the idea of like what AI could do. This was kind of before it was really cool the way it is now. But I started by writing some pseudocode for a artificial neural network. I was reading books, reading articles, but essentially I'm self-taught when it comes to anything related to AI. I listen to the greats. I try to read the papers, but also not being a mathematician, that's hard for me. I'm a musician, I'm a drummer, which means I can count to 4 really well. So math is not a strong background for me, but I manage software development teams. I design digital signal processing solutions for all types of automotive, aviation, consumer electronics applications. I've been part of medical studies. I've published some papers using acoustics in medicine, and I have a couple of patents to my name. So, I've been around the block. I earned my gray beard, but it is not in mathematics and it's not in AI. That's always been a hobby for me and something that I've just sort of always loved from when I was young and building robots before I got into music, and that captivated my attention for many years. So with all that being said, I am leaning very heavily on agentic coding tools like Gemini. I was using anti-gravity first in this project, and then you'll see me transition into Claude Code. So that's very important for me to be able to realize a lot of these very interesting ideas and to kind of 10x my abilities as an engineer and try experiments that would cost millions of dollars in other scenarios. And I very much recognize that not everybody likes the idea of AI coding tools, especially if they've been developers their whole careers. So I've talked to our developers about what it means to them to use AI coding tools, and we have good conversations about how it really sort of extends your abilities. You're never going to be able to build something truly complex and revolutionary unless you have some good technical background to go behind it. So I consider AI coding tools to be an extension of my abilities as an engineer. This allows me to try these sort of moonshot ideas that wouldn't really be possible any other way. So in order to get past my limitations with mathematics, I treat each algorithm or each mathematical concept sort of as a black box. This is what I do when I'm engineering anything. And it's all about, what are the inputs? What are the outputs? Am I getting the results that I'm looking for? Is this the right mathematical approach? So I understand what math can do, but I can't do the formulas myself. I build visualizations to understand how this formula works, how it works in the context of the thing that I'm building. And that's what I've got to work with. I would love to be working with mathematicians that know more than I do and are experts in this field. But right now I'm building it by myself, and I look forward to collaboration. Hopefully, if this sparks some interest with the community and they want to jump in, please. I can't do this all by myself. So this is one of the reasons that I'm open sourcing this project, and I was able to get permission to do that from Bon Jovi Media and Technology, because using AI coding tools means I am absolutely standing on the shoulders of giants much taller than myself. I recognize that. Therefore, if there's any bit of inspiration that I can lend back to the community, I'm going to do that. That's why this project is having an Apache 2.0 license. If you use that code, you are granted a patent. It's open source in a very powerful way, so that if there's an inspiration, then you can pull a piece of that code and it works for your project, please do it. But read the README. There's some important points in there that I'd like to make very clear that I'm not going to talk about on video. So with all that being said, I am definitely going to explain things poorly. I'm probably going to misstate the purpose of some of the algorithms that I'm talking about, especially when it comes to the math. Correct me. That's fine. That's what the comments are for. I come into this idea humble and ready to receive, constructive criticism. You can beat it up all you want, but, I think the best way to have a comment about whatever it is that I'm presenting is to send me a PR. It's open source. Go try it out. Please improve it. I would love to see if any of these ideas really hold water and can move some of the ideas of active inference and embodied intelligence forward. So that's the purpose of this. Let's build something that's really, really cool, that can interact with our world in different ways than what's currently being explored right now. So really, this is a story of relentless critical thinking and going back to good scientific philosophy, being humble, checking your ego at the door, and always trying to prove yourself wrong. You're going to hear me say that over and over again. Applying good skeptical concepts to science and learning and just, discovering while building. That's what this is all about. Let's start it off by seeing the very first pass at the episodic predictive module. It's probably going to start off with a different name. I think I was calling it some other acronym besides EPM, but you get to see this from the beginning and how it all evolved and became what it is today. So check it out. All right, everyone, this is a brief introduction into this new project that I'm working on called xaq-ai. The idea here is to create some kind of a knowledge graph builder that can work without supervision, right? Or minimal supervision. So we already know that, some of the issues with reinforcement learning and supervised learning is that you need a ton of data in order to train a classifier or an event detector to do what you want it to do. Well, I'm trying to reverse engineer that, and I was really inspired by Jan LeCun's last paper about JEPA and an old paper called Playful Machines, where it has this time loop error idea. So I wanted to combine those two ideas together to create a knowledge graph builder for audio. So I think a lot of really interesting work has been going on right now for video, especially on Jan LeCun's side. Obviously, he's a big inspiration of mine. So I want to try to do this for audio and extend that kind of capability, build up a UI that makes it super easy to use, and see if we can build these kinds of knowledge graphs using a UI and without any kind of prior knowledge of what the audio actually was. So let me just run through this UI here, and I think I can just start using the example. So when you first launch xaq-ai, if we look here on the left-hand side, we've got the ability to save and load the state. But mostly, let's look at these different configurations that we have here. So the idea is that we have an encoder, sort of like a generic encoder that can create a vector of 768 variables that can change depending on what the input is. And it doesn't actually matter what they are because it's going to create a node based on that embedding, right? So we can kind of look at the encoder here. Right now I've got a pre-trained encoder. We can look at the audio waveform here, and then we can look at the predictor dynamics. So what I'm going to do is just start off our debug audio source, which is a 440 hertz tone and then a noise, right? Or white noise. So it's noise, tone, noise, tone. It's very simple. If I hit play, you can listen to it. So that's our audio source that we want to classify. I'm going to mute it for now and just let it run. So you can see that it created a node already. So it's created a node because the predictor over here detected that something changed, right? So this is a big part of it. First, we have the encoder, and then a predictor that's looking for anomalies. And then when an anomaly is detected, it creates a new node. So right now we're watching those predictor dynamics drop, and now we see some new nodes popping in. So as soon as that floating threshold came down low enough, and the surprise was detected based on our very simple, it's just a little multi-layer perceptron that is our predictor. I do have some other predictors that are in the works, but we can adjust the learning rate of the predictor, and we have some ways of changing that, but that's not really the important part. That's just to detect if something new has happened, right? It's the encoder creating these nodes on the knowledge graph, right? So if we actually watch what happened during this session here, if I unmute, so you see, let's look at the waveform so we don't have to listen to the beep and the psh. So while the tone's playing, this node's lighting up. It's very, very isolated because a tone is very static for this encoder. And then when the noise happens, it's kind of floating around the group of nodes over here. So there's actually some physics that's going on in the background to group these nodes together into a knowledge graph where, if there's something different about that particular patch or that particular embedding, it's going to move the node farther away than something that's very, very different from it. So if you think about it, like the tone is over here on the right-hand side and the noise is over here on the left-hand side. So you can see here you've got some dynamics that you can tweak, but really if we just watch it, we can see the knowledge graph being built. And the reason there's some new nodes popping in is that we got a buffer size, and our buffer size is set here. The chunk size is 100 milliseconds, right? And the reason that new nodes are popping in is because it's still being surprised. So remember, the encoder is not smart. It just generates embeddings. And the predictor is also not that smart. It's just detecting surprise, right? Now, the surprise is suppressed if the node has been baked. So you can see that these nodes that have turned yellow have been baked because they've hit a 100 trigger threshold, right? That's sort of our long-term memory. So when something that has been happening over and over again is triggering the same node over and over again, it starts to build the concept that, okay, this is something I need to remember, right? And these other nodes are being created, but they're not hitting all the time. It's really just the variation of where the noise is transitioning into the tone inside of that buffer. So every time it changes, it is surprised, but they're not really important, right? And I'll show you how to get rid of that in a second. But if we just sort of look at the various controls here, now that you can watch this knowledge graph being built of noise on the left and tone on the right, now we're kind of getting an idea of how this thing really works, right? So if I just go down the list of options here, so we can save and load the state, we can export the weights of the encoder, and I'll show you about how to do that later. We can record. I'll show you about how that works. But really on the highest level, you can set your input device and output device. You can run this on real-time audio, or you can load WAV files, mute the output like we have it right now. Chunk size changes the window of sound that's being fed into the encoder. And then we have our predictor, which is giving us that time loop error. We have several different options here, but right now I'm just using that stateless version. We can also open up our advanced sensors for when we're using an encoder that uses spectrograms. We have some adjustments for the spectrograms here, but right now we're actually using a wave, this Hubert pre-trained wave to vec type encoder, right? Like I said, we don't care what the outputs are. We just want to look at those embeddings. And on the right-hand side, we have all of our node dynamics. So the first thing we can adjust is the threshold response, which is the pink line here. So if I slide this up, the multiplier raises the threshold, right? So it stops being as surprised. But really, like 1.5 is a good spot. So you keep getting surprises. You keep getting new nodes triggered and seeing if it's a novel node or not. This adaptation is how closely it can follow the predictor's output, right? So if I turn this up, it's going to try to follow it more accurately, and it's going to result in less surprises. You can see that's actually responding more as it goes up and down. So these defaults are good though. We can just leave those the way they are. Concept sensitivity is, if you want to think about this embedding space that's being output here, these like groups of numbers that represent a sound, we can fit those more or less into a new node by making it more or less sensitive, if that makes sense, right? So we can, if we draw a circle around all those numbers, we make it less sensitive. It's going to create less nodes because they're going to fall into that same bucket. And you can see now this graph is staying very steady, right? Because all of these events are actually falling into nodes that have already been baked, and it's not that sensitive. But if I slide this number up, you can see, it's picking up a lot of novelty, right? So this is a very important slider for, as you've got your concepts sort of becoming more and more solidified, you can turn that sensitivity down because now you're building your knowledge graph and it can stay a little bit more static. Baked node safety, that's what we were talking about here. If it's falling in, if a node that is has been triggered, that's been baked, it actually pulls the surprise level down for that instance, so it doesn't actually raise the threshold, and it's basically ignoring stuff. It's like, how much can you ignore sounds that happen that are falling into nodes that already exist, right? Because it's not new, it's not novel. We don't need to learn anything about that. It doesn't need to create a new node. It just forgets about it. And then the memory baking. So right now I have that set to 100 hits. That works out pretty well. If it's been triggered 100 times, it gets the yellow circle. It's been anchored. So auto anchor kind of like locks it into place here so you can start to visualize your knowledge graph. And then you can freeze the learning eventually. Active decay is why you see a lot of these older nodes sort of fade off into the distance, right? They were triggered. It was just because of that one time that the transition between noise and tone happened in a certain place, but who cares, right? You can have those fade away into the distance because we just want to forget about them because we feel that they're not important. Now you can turn that off if you think that everything's important. Let it build a lot of nodes. Let's see if they can survive. Let's see if they get baked, right? So the semantic layout, this gravity, this has a way of basically grouping the nodes more or less together depending on how similar they are. And so does this clustering depth. So if we change that a little bit, we can see those dynamics change. We're not changing as much because we have auto anchor turned on and these nodes are getting anchored in space, right? And then the concept spread is like how much space do you want to have? Do you want to use in order to build out your plot? And you can see as I change it, the nodes that are not baked yet or move, but the ones that are already baked are locked in place. If I turn that off, turn off the auto anchor, yeah, you can see it start to form a new shape now that they're not anchored anymore. It doesn't really matter. This is all about building something that helps you represent the thing that you're trying to represent. So I have to stop the video here because I start mentioning some things that are proprietary to Bon Jovi Media and Technology, which is a sponsor of this project, xaq-ai. But in the next video, you'll see me go into much more detail and start to explore what's possible with the EPM.